Similar to the work done by a constant force over a segment, the work done by a constant force over any curve is given by the work of a force F when its point of application moves from A to B is equal to F vector dot AB vector. Where do we witness such case? We witness such case in the work done by weight, for example. The weight, close to Earth, is a constant force. Its direction is always vertically downward, and its magnitude is m times g, which is a constant value. For example, we throw a certain body in the air. It describes a parabolic trajectory, passing through points A and B, for example. The body is under the action of its weight, mg. Now we're going to determine the expression of the work done by the weight. The work done by the weight, which is a constant force, is found by the expression. It is mg dot ab. To simplify things, we're going to divide the vector ab into two vectors, ah and hb. So we get mg dot ah plus hb. This is equal to mg dot ah plus mg dot hb. But mg is perpendicular to ah, so their scalar product is 0. We get 0 plus mg dot hb, which is mg times hb times cosine of the angle between mg and hb. Mg is downwards, whereas hb is upwards. The angle between these two vectors is 180 degrees, and the answer is minus mg times hb. hb is also the height between A and B. HAB is the distance between the levels of A and B. HAB is the distance between the levels of A and B. This is the level of B and this is the level of A. So the work of mg when its point of application moves from A to B can be written as minus mg times HAB. What can you notice here? The work of weight, as you notice, is independent on the trajectory. It only depends on the height of the climb HAB. Why did you obtain a negative sign? Since during the body's climb in this direction, the weight acts in the general opposite direction. Then the weight is a resistive force. Hence the work is resistive and we get the negative sign. Let's take another example. If we throw the body like this, from point A to point B, if HAB is the height between the two levels of A and B, we can simply prove that the work of mg when its point of application undergoes a displacement from A to B will be given as follows. plus mg times the height between A and B. Note that these two expressions have opposite signs. Why did we get a positive sign here? Since during the descent of the body, its weight aids or helps the fall, then the work of the weight is motive. Hence, we assign a positive sign to the expression. So we have two cases. The work of the weight is either plus mgh or minus mgh. Plus mgh during the descent of the body, minus mgh during the ascent of the body. Let's solve an application. Consider a body of mass 2 kilograms. This body is moving along a track in the vertical plane and the body is descending. We want to determine the work done by the weight when its point of application moves from A to B. We also want to find the work done by weight when its point of application moves from B to C, and finally the work done by the weight as its point of application moves from A to C. Let's start by the work done by mg when its point of application moves from A to B. The work of the weight is the work of a constant force that moves on a certain curve. So it is either positive or negative mg times h between A and B. Note that m is equal to 2 kilograms and g is equal to 10 meters per second square. This is the weight mg. The body descends, then the weight is a motive force. The motive work is assigned a positive sign. Remember that HAB is the height between the horizontal levels passing through A and B, which is 12 meters. So we get 2 times 10 times 12, which is 240 joules. Now the work of mg when its point of application moves from B to C. Here the body is rising. The weight acts in a general opposite direction to motion. That is to say, it is negative mgh bc. This is equal to negative 2 times 10 times the height between B and C. It is the distance between two horizontal levels, one passing through B, the other passing through C, which is 4 meters. And the answer is minus 80 joules. This is a resistive work. Now we have to calculate the work of mg when its point of application displaces from A to C. Pay attention here. As the body moves from A to C, the height between A and C is HAC. What is this height equal to? It is equal to 12 minus 4, which is 8 meters. From A to C, the body descends. Then its work is motive. We write it as plus mghac. This is 2 times 10 times 8, which is 160 joules. This is the work of the weight from A to C. Another application to calculate in two different ways the work of the weight mg of a body as the body moves from A to B on an inclined plane that makes an angle of 30 degrees with the horizontal. The mass of the body is 4 kilograms, AB is equal to 10. The first method, the work done by mg is equal to mg times the height between A and B. It is a positive work since the body is descending. What is the height between H and B then? It is the distance between the horizontal levels passing through A and B. This height is AH, for example. To determine HAB, consider the triangle AHB. Sine 30 degrees is equal to the opposite, which is HAB, over the hypotenuse, which is AB. So HAB equals to AB sine 30. This is equal to 10 sine 30. The answer is 5 meters. As a result, the work is equal to 200 joules. Another method. We use the definition of the work of a constant force over a segment. This is equal to the force multiplied by the displacement multiplied by cosine of the angle between the force and the displacement. What is the angle between the weight and the displacement? This is the displacement, the dotted line from A to B. So what is the angle then? Here it is. This is 90 degrees and this is 30, and the angle becomes 60 degrees. As a result, 4 times 10 times 10 times cosine 60, the answer is 200 joules. This is the second method for determining the work of weight. Now to find the work of the weight, this figure shows a body held by a string in the vertical position. The body moves from A to B over an arc having a radius L equals to 2 meters, which is the length of the string as well. In this position, the string makes an angle of 40 degrees with the vertical. To find the work of the weight of the body attached to the string when its point of application moves from A to B, we consider one method. The path is not straight for applying mg times AB times cosine mg AB. For a non-straight path, we use either positive or negative mg times h AB. What is the sign of this work? The body rises from A to B. The weight of the body acts in the general opposite direction, so the work is resistive, and it's negative mg/h/ab. Now to find the height between A and B, these are the two horizontal levels passing through A and B, and the height between them is h. Make the orthogonal projection from B to OA. OA is always equal to L. We have to determine OH in order to find the height H, which is HA. In triangle OHB, OH is the side adjacent to the angle 40 degrees. So cosine of 40 degrees is equal to OH over the hypotenuse, which is OB. So OH is equal to OB cosine 40 degrees. OB is the length of the string. This is equal to 2 times cosine 40, which is 1.532 meters. So to calculate HA, we go back to the figure. It is OA minus OH. 2 minus 1.532. The answer is 0.468 meters. This is HA, which is the same as HAB. Now the work of MG when its point of application moves from A to B is equal to minus 0.1 times 10 times the height between A and B, and the answer is minus 0.468 joules. This is the work of the weight when its point of application moves from A to B, which is a resistive work.